Hi everyone, welcome back. This is Professor Herring. In this video, we're going to continue looking at different ways to represent molecules. Specifically, we're going to learn how to draw and interpret carbon backbone or skeletal structures when describing organic molecules. Let's begin. It turns out that there are literally thousands and thousands of different types of organic molecules. And we're going to talk about why this is the case. Why is it that organic chemistry is such a diverse field? It turns out that the reason for this is, there's multiple reasons for this. One is that carbon is able to form very strong, stable bonds with elements in general. Because these bonds are so strong, it means that these molecules will persist in nature. We also know that carbon has a valence of 4. Because it can form 4 bonds, this can lead to lots of variety. And then finally, due to carbon's size and the fact that it has such a high valence, it can form double and triple bonds. So these 3 ideas together mean that when carbon forms molecules, that it's able to form so many diverse types because you can bond with other elements, you can bond in differing number of bonds, and these bonds are very stable. Because there's so many different types of organic molecules, we need to be able to classify them, to put them into categories. The most basic classification is called the hydrocarbon, and that's where it's an organic molecule that contains only carbon and hydrogen. That's where the term hydrocarbon comes from. A second general type is where we have other heteroatoms that are bound. So if you have nitrogen or oxygen or fluorine, etc., bound to carbons, then these have their own names as well. We'll talk more about these groupings later in the semester, but it's important to see that there's a distinction between hydrocarbons and then other functional groups. And there's a variety of ways in which we can represent organic molecules. One way is by using the molecular formula in the name, as you can see up in the top right-hand corner. This doesn't give us much information, but it is the simplest way to communicate about the molecule. Beneath that, you have the Lewis structure. This shows all of the bonds between all of the elements. And you can see, as we're starting to draw larger molecules, that it can get quite complicated and time-consuming to do so. Beneath that, you have the condensed molecular formula, and this shows bonding patterns as well, just as the Lewis structure does, but it's a little bit simpler. Beneath that, we have the ball and stick and the space filling models. These are more accurate representations, especially the space filling model, but they would be very difficult to draw, and they hide some of the interactions or some of the bonds that exist. Our final type is what we call the skeletal structure. This contains all of the information as the Lewis structure and tells us about what element is bound to what element, but is a much simpler way to draw. And we're going to show on the next slide how you can go about doing this. So let's say that you wanted to represent isopropyl alcohol. On the top right-hand side, you have the Lewis structure. And Lewis structures show lone pairs, they show all the elements involved and the bonds. On the bottom right-hand side, you can see that we've omitted the electrons and we've omitted most of the hydrogens and all of the carbons. And so we follow these following rules for drawing and interpreting skeletal structures. First, lines are represented by covalent bonds. This is the case as well for Lewis structures, but in this case, each of these lines represents a covalent bond. Next, the intersection of those lines and the termini represent carbon atoms. So we always are going to be hiding the carbon atoms within the skeletal structure. And that makes sense, since mostly it is carbon and hydrogen, we can simplify them by understanding about the termini and the intersections. Third rule is that hydrogen atoms are going to be bound to carbon atoms to satisfy the octet, but are not shown. So what we saw up here was that we had 3 hydrogen atoms on this carbon, and they're still present in the molecule on the bottom, but they're not shown. Again, just as a way to simplify. The fourth rule is that heteroatoms are shown, and the hydrogen atoms are shown on them. And that's very important because of the last rule, in that we don't show the lone pairs. So if we didn't show the hydrogen atom here on this oxygen, then it would be implying that there's 3 sets of lone pairs. And so we have to be very explicit in demonstrating when there's hydrogen atoms on the heteroatoms. And then finally, if we did have a formal charge, +1 or -1, then that would be shown explicitly in the skeletal structure. On this last slide, you see 3 more examples of skeletal structures with their Lewis structures beneath them. You can see that the Lewis structures really are a more cumbersome and time-consuming way to draw things out, and it's much more pleasing to the eye to look at the skeletal structures while we still get all of the same information as the Lewis structures. So take a couple minutes to look over these structures and try and interpret them and see how we go from the Lewis structure to the skeletal structure. Once you're done with that, that's the end of this video. So thanks for watching, and if you have questions, be sure to ask on Piazza and office hours or recitation. Have a good day.